Hi everyone. Today we're going to be talking about energy and voltage. We've learned a bit about electric fields already. We know that when a particle is in an electric field, it will be attracted or repelled by the charge that's creating that field. So where does the energy for this movement come from? Well, when a particle is in an electric field, we say that it has electric potential energy. Now, when a charged particle experiences a force on an electric field, it's going to gain or lose energy, right? If the field is slowing it down, it'll lose energy. And if the field is speeding it up, it'll gain energy. So energy is conserved, that is, it can't be created or destroyed, which means that if the object is speeding up or slowing down, then it must have potential energy. That is, the sort of energy stored up in the electric field. So this is similar to gravitational potential energy, which you would have learned about already. Remember, if you suspend something above the ground, it has the potential to fall down and gain kinetic energy. So we say it has potential gravitational energy. In the case of electric fields, we don't have the potential to fall down, but we do have the potential to be attracted or repelled by a particular charge. So when a positive charged particle that has been brought close to a negative particle, it has the potential to fall towards that particle. So if I were to let go of this positive charge here, it would be attracted to the negative plate. So we can use this potential, that is the tendency of this charge to fall toward the other charge, to produce electricity. All we need to do is make the charged particles want to fall in a particular direction, as it were. Now, the magnitude of the potential energy is given by force times distance. The force in this case is, of course, going to be QE. That is the electric charge of the particle multiplied by the electric field strength, multiplied by the distance it's able to fall. We used something similar to this to find out gravitational potential energy. Once again, we used FD, but in gravity, the force is mg, and d is instead represented by h, height. So that'll be mgh. In this case, we're going to leave the distance as d, and the force is going to be the force due to the electric field, which is QE. Make sense? Now, 2 points in an electric field can have different potentials, is what we call them, instead of saying they have different heights. So we can visualize the potential something like this. We might have something with a high potential and something with a low potential. We don't know exactly what numbers to assign to this potential, is the thing. Now, a positively charged particle will be able to fall from a high potential to a low potential. It'll have a large amount of potential energy at the high potential, which means it'll want to roll down the hill to the low potential. It'll be repelled by the positive plate and attracted by the negative plate. Now, the potential difference between 2 points is called the voltage, and that's what this is here, the 240 volts. Now, I mentioned before, we don't know exactly the rating of how high the high potential is or how high the low potential is. For all we know, the true 0 point might be all the way down here somewhere. But the point is, the difference in potential between the high potential and the low potential is a voltage, right? That's how far a charged particle can fall. Now, algebraically, we represent a voltage with an italic V and measure it in volts, which is an upright V. They're both capital V's, so we have to be careful to distinguish between a number of volts and the unit of volts. The magnitude of the voltage between 2 different points in a uniform electric field E is going to be V equals ED, right? So if I were to take 2 points in this electric field separated by D, then the voltage between them, that is the potential difference between them, is simply going to be the strength of the electric field times this distance. And that'll get the height of the potential hill between those 2 points. Now, between 2 points of different potentials, charged particles will try to roll downhill. They'll try to go from the high potential down to the low potential. Now electrons are negatively charged, which means they behave oppositely. Instead of rolling down the hill, they're like helium balloons floating up to a diagonal ceiling. So they try to fall up, as it were. So they fall from the low potential to the high potential. Remember that electric field strength always points from positive to negative, and negatively charged particles, like electrons, will go against that. So the movement of charged particles is what we call electric current. Now the work done on a charged particle can be determined by the difference in potential energy. We can say the work done, we could also say energy, but I don't want to get it mixed up with electric field, equals Q, the charge on the particle, times the change in voltage. That means that if we want to move a positively charged particle from the low potential up to the high potential, we have to expend this much work, where delta V is the height of the potential hill that we're climbing up. The potential energy is converted into kinetic energy when we're going towards its destination. So if our particle has very high potential energy and we let it go, then it will roll down the hill and gain kinetic energy while it loses potential energy. Now, here's the relationship between energy, charge, and voltage. 1 volt is the potential difference through which a single charge, exactly 1 coulomb of charge, loses 1 joule of energy. So if we expend 1 joule of energy on a 1 coulomb charge, we can move it through a voltage of 1 volt. So 1 volt equals 1 joule per coulomb. It takes 1 joule for every coulomb we want to move through 1 volt. So higher voltages will, of course, produce particles with higher energies, because the amount of energy that they gain is proportional to the voltage through which they're crossing. Right, hope that all made sense. We've been learning about electric fields and how we measure them, things like voltages and energy. Let's go on to some questions to check if you've got it straight.